And welcome back to another teardown. Today we have a Digilog measurably better voltage indicator PL107N. So without further ado, let's get inside. Right, now the easy way in is you squeeze down on here and that slides the battery cover off. Then pop out the batteries, and that one gets a bit stiff, so you have to pull it out. It's obviously designed for smaller AAA batteries. And then this bit comes out. Now it doesn't always come out. There's a catch here, and that catches on a piece of plastic, so as you pull it out it catches. If I bring it up, you see it there, that little indent, that catches in there, and there's a little rubber button. So that's just the empty plastic shell now. Bring this back, focus in on that. I'm saying that's a little catch. That's it's obviously a bit bent. It should be sticking out a bit more. But and inside we have obviously the probe, but there's an LED. It takes two batteries, it's got a buzzer on this end, and then we have the touchpad and then the circuitry. So let's bring in the microscope, and we'll pop the microscope up. Where's it gone? There we are. Pop that up, move that there so you can see it. Alright, that's better. Seem to have some green paint on there. Some green paint on there. We can't quite make it out. It's a 74HC14D. And then we start from, go right to left. We have a transistor, 2A, 470 ohm resistor, small signal diode, a capacitor, a 205, so that's a 2 meg resistor, 395, so 3.9 meg, unknown capacitor, 3.9 meg, 2 meg, very high values. But let me get 820k, 470k. Is that another 3.9 meg, three more signal diodes, two more transistors, a 1k resistor, the 470 ohms of 470 ohms of 47 ohm, and 500 meg, 50 and 7 noughts, 500 meg, and then we're on to the touchpad, and finally the probe with the LED on the other side. No other components on here, apart from when you get down to here there's the speaker, or the squeaker, can't really call it a speaker. So that's having a look at the components so far. We'll take the microphone out, the microscope out of the way, get rid of that. And I don't know if people want to play along at home. There's the tracks. So you could take a still of that if you want to. But I'll try and reverse engineer it. So we'll come back when I've got a circuit. Right, here we are, the circuit. You have a probe in its little cover. The probe's pulled down to the negative rail of the battery by a 50 meg resistor, and then there's a 3.9 meg resistor feeding it into the input of the Schmitt trigger inverter. Now, this circuit does go to show why you should never leave an input of a logic gate floating, because effectively this is floating. It's 50 megs, so it is floating, and they're using it as an amplifier. As you bring anything with a sniff of mains on here, then this starts triggering, which then triggers that one, and so coming out of here we get a nice strong square wave at 50 hertz or 60 hertz if you're in America, and then it hits this, which is a charge pump. Each time that level goes high, current is pushed down through the diode into the capacitor, charging the capacitor up. When it goes low, current from the capacitor flows through this diode down into the low, and they're different values. So looking at this, it should discharge faster than it charges up, so it should shut up as soon as you move the signal away, and that's what happened. That's what's happening here. In the circuit you get a kind of exponential curve here, but on KiCad I can't find a way of doing that easily, so I'm just showing it as effectively you touch the probe and the voltage slowly ramps up, and then you let go and it dies away. And here again, this is diode connected to this, which is basically an oscillator made out of two inverters, because you need about 360 degrees to get an oscillator running, and you get like 90 degrees through here and 90 degrees through there. Well, that's not 360, 180 degrees. So you get a kind of a feedback which makes it oscillate, and they're very high values. I can't measure the capacitor in circuit, and I don't want to take it out because the probe still works, and so it must be sort of high. It must be in the microfarads. It's quite a large body capacitor, so I would say it's in like the 10s to 100 microfarads, or maybe 10 microfarads. And so that is producing effectively a square wave. When that voltage here is high enough, current stops kind of being, this input stops being pulled down because current has stopped flowing through the diode, and so it's then kind of, that becomes a high impedance and the circuit is allowed to oscillate. And it's the same here. When the output here is low, current from the input is pulled down, so the input will be about 0.7 of a volt, or and as soon as it goes high, that goes high, and eventually becomes a high impedance again, removing a kind of current drain onto here, and that allows that again to kick off and start oscillating. And this one oscillates with a much smaller capacitor, and so it's a higher frequency. So here I've just shown it as like spikes, and basically it bursts to the high frequency, then it shuts up, then it bursts again, and you can see that signal's taken down, fed to that transistor, which drives the buzzer, so the buzzer would chirp. Coming down here, the low frequency signal goes to this transistor, effectively turning it on and off, which drives the light and flashes the light. And as you can see, the battery goes straight to the VCC pin of the 74HC14. So the whole of this circuit up here works regardless of pressing the button or not. So that is constantly, if you bring a main signal near it, tweeting, it's just, you can't hear it and you can't see it. When you bridge the touchpad with a little carbon film pad, you drag the base down, turns the transistor on, puts power onto these, so if there's a signal here, the buzzer will start sounding, and if there's a signal here, the LED will start flashing. If there's no signal here, they've used quite a sensitive LED, and as you can see, they've bypassed the transistor with a resistor. So when you press that with no signal, the transistor is turned off, the current flows through the bypass resistor down through the LED, and it brings that voltage up to about mid-rail, to about 1.5 volts, which is enough just to turn the LED on at a kind of a reasonable brightness so you can see it through the plastic. So that gives you the indication that your battery's working, because the LED will light up, and then as soon as you get a signal near here, this all kicks off, and of course you get the flashing light and the buzzer sounding. And in a bit we'll have a look at the circuit in action, and we'll see that, you know, that doesn't look like a ramp, it looks like an exponential ramp and decay. That doesn't quite look like, it looks like a square wave, but it has some of the high tones in it because of the sort of feedback and the power side, and this side looks slightly different, but it's, you get the idea, you know, low frequency flashing the light, driving the high frequency oscillator, making the chirp. Right, so I hope that helped with the understanding of the circuit and you found that interesting. So let's go and have a look at the actual board on the bench. Oh, and a side note, this circuit around here is so sensitive that if I feed the battery from any of my mains power supplies, it chirps, it won't shut up. So I had to feed it from a battery to take the measurements, because mains supply, and it's just enough interference on the mains to kick this off. Right, I'm going to have a look at some of the traces on the board, and I was going to link the Hangtech scope to the PC, but it was absolutely useless. It just kept latching, falling over, resetting the scope and updating so slow. I've gone back to the idea of I'll just stick the microscope, you can see the lead across there, facing screen, and we'll just record it with the microscope, because the interface to the scope is absolutely rubbish on the USB. So need a better scope. If any scope manufacturers are out there listening or watching. Right, so what I thought I'd look at first is this is powered, the actual chip here, the inverter, is powered all the time. Only the driver for the light and the sound are switched by the button. So if I move that over a bit so you can see the light is off at the moment. If I press the button, you'll see the light come on. But without pressing the button, if I put the scope on here, you'll see as I bring my hand in and bring some main signal towards it, if I touch the tip, there it goes, it starts to oscillate because it's picking up the mains. And then on the other one it's doing the same again, but it looks sort of slightly different because of the way the circuit's configured. So that shows you, if I actually slow it down to about 4 milliseconds, you'll actually see that what comes up is 50 Hertz. Now it's a 50 Hertz square wave. If I actually hold the tip, you see that there's the mains it's picking up off me. So it just goes to show how sensitive an open input to a logic gate is, because they're using the logic gate as an amplifier. They're just letting it float, pull down with about 20 or 30, no, pull down with about 50 meg. So you've seen the circuit diagram by now. So we'll just look at, you know, what's happening here. You can see there, and as I bring my fingers in and touch, the voltage goes up and it goes down. And all this does is when that voltage gets to a certain point, so if I put it on the drive to the speaker, when I touch the tip, you'll see the two oscillators running, the slow one and the faster one making the squealy noise and the slow one making the flashing and turning it on and off, pulsing it. And the LED, which is driven from there, you can see it's got the square wave going to it as well. It should be slightly different, but you're seeing sort of mix and matches. They're you know, it's picking up both oscillators running together. You might even find if you put the oscillator going, it appears. Oh no, it doesn't appear on the 5 volts. No. But there we have it. That's sort of the main important bit. Is it's picking up a square wave, feeding the square wave into a peak detector. When the peak detector rectifies the square waves coming in, and when the voltage on the capacitor reaches a certain point, that opens the trigger or allows the low frequency oscillator to start, which consists of two inverters. When that one starts, it triggers the higher frequency one, so when it's in a certain state, the high frequency one will go, and then when it changes state, the high frequency one will stop. And so you get a burst of the high frequency. And as you can see, it's all working. There's no sound coming out, and there is no light coming out, because that button controls the power. When we look at the circuit, that button controls the power to the light and the sounder. And then when you press the button, if we look at the output to the LED, you'll see it's sitting at 0 volts at the moment. If you press the button, it floats up to mid-rail, which puts the light on dimly, and then when you touch it, it switches it between mid-rail and high, so it goes bright and then dim again. So very clever use of the circuit. Well, I hope you found that interesting, and if you did, click on the subscribe button, hit the like button, click on the bell for more, and I'll catch you on the next one.